welcome everyone to the second edition of this semester's Hyperloop Seminar. I'm happy to welcome everyone. And so today we have actually one guest, so we have lots of time for all of your questions. So for once, I hope we can answer all of them because we have a lot of time. And yeah, so remember, you can put your questions directly into the Zoom. So there is this Q&A button where you can pose all of your questions. You can also make them anonymous. And yeah, so I think we already start with our first guest, and Daniel will introduce him to us.
Thanks, Andrea, and welcome everyone to the Hyperloop seminars. Today with us, we have the pleasure to welcome Nader Zainali, who has been a former colleague at ours at EuroTube. He conducted his master thesis jointly with Hochschule Luzern, and today he will give us a deeper insight in his studies on aerodynamics. Specifically what happens when a vehicle is traveling on high speeds in a low vacuum environment, when we take into account parameters such as blockage ratio and the shape of the vehicle. To give a bit of more context, Nader did his master's degree at the Hochschule Luzern, and since the beginning he focused on CFD and numerical simulations. This has been his focus, and this is what he has been developing all along his master thesis. And it has been proven that with this nice master thesis, he's very well prepared now for the next stage, and hopefully also making an impact in the industry. So without further ado, Nader, I would leave the floor to you, and thanks for joining. We're really looking forward to your presentation.
Well, thank you, Daniel, for the introduction. Yeah. So hello and welcome, everybody. From my side, it's my pleasure to be here and present my work, my master thesis. As Daniel already explained, and as you can see, the topic is about aerodynamic analysis of drag force for a vehicle inside a low pressure tube in Hyperloop concept. Specifically, we were focusing on reflection shock wave, but we also did the analysis of the incident shock wave and effect of blockage ratio and so on. So for today's talk, I will start with motivation and objectives of my thesis, briefly about simulation setup, different models that I used for my simulations and the results, and also the retardation effect, which is the main effect of the reflection shock wave, and finally the conclusion. So as you know better than me, that Hyperloop transport system relies on mainly two technology: magnetic levitation known as maglev system and vacuum train known as vac train. My work was included in the second category. So the main advantages that we can get from vacuum or a near vacuum condition is a less air friction, which result in less drag force and of course less energy consumption. But in this condition, the compressibility effect of air is being highlighted, which cause generation of normal shock waves. And basically, normal shock wave is being generated as a result of choke condition, which is occurring at the minimum area. The red markers, okay. The red markers here. And the mass flow rate becomes constant, and the air will be more accumulated in front of pod than going through a bypass region. And the accumulated air will increase pressure, density, and temperature, which cause a normal shock wave. The way that we characterize the strength of choke condition is through the blockage ratio variable, which is nothing else than a fraction of pod and tube cross-sectional area. And then we can relate blockage ratio to the speed of pod and Mach number through the contour width limit, which gives us two region choked flow region and no choked flow region. And as you can see, the green and the red spots are the two blockage ratio, different blockage ratio, which were my test cases, which both of them landed in choked flow region. And speaking of the objectives, obviously we should start with analysis of incident shock wave, which in this case we call them leading incident shock wave, LISW, when the shock wave which is being generated by movement of pod and choke condition. And then we can evaluate the strength and the speed of shock wave and also have the evaluation on the drag force. But as the shock wave is being generated, is moving towards the tube end wall, and at some time it hits the end wall and reflected back, which we call it leading reflection shock wave, LRSW. And here we develop a simulation protocol to actually mimic the interaction between the incident shock wave and the tube end wall, consistent with the incident solution. And then after initialization of the reflection wave, shock wave moves towards the pod, at some time hits the pod, new choke condition occurs, and the second reflection wave is being generated and moves towards the tube and wall again. And then we can have evaluation of the drag force and retardation effect. So the simulation setup in tube stationary frame, you can see the dimension of the tube and two diameter for the pod, which corresponding to two different blockage ratio. In my simulation, the pod is moving with speed of 200 meters per second, and you can see the condition inside of the tube. My simulation is conducted in pod stationary frame, axisymmetric pod stationary frame, meaning that at inlets, we have mass flow inlets, boundary condition, outlet is pressure far field. And if we precisely define the Mach number at the inlet and outlet, then the simulation in pod stationary frame will be equivalent to moving pod inside of a stationary fluid. So the first model that I use is implicit model without viscosity, where I evaluate the effect of blockage ratio and use density-based solver. And the second model is viscous model, which we add the viscous effect into our consideration, and the simulation is being done for only one of the blockage ratio. And we also change the characteristics of the boundary condition for walls of tube and pod. And we use transient SST turbulence model for solving Grand's equations. So the first result, of course, is solution of the incident shock wave. As you can see, the two blockage ratio. And the pressure in front of this higher blockage ratio, of course, is higher than the lower blockage ratio. And the second point is that the shock wave in the second case is ahead of the first case. So here I have an animation. I think it hopes it works. Yeah, you see that the bow shock turns into the normal shock wave, and for higher blockage ratio, it is speed up, and the numerical solution for pressure, temperature, and Mach number, it also shows that for a higher blockage ratio, we have higher pressure in front of pod. And it, in another word, is that as we increase the blockage ratio, the strength of shock wave also increases. And by calculating pressure gradients, we were able to numerically detect the location of the shock wave over time. Then we were able to calculate the speed of shock wave. For this case, for case blockage ratio 0.81, you see that the speed of shock wave reaches to 251 meter per second, which is 51 meter per second higher than the speed of pod. And to analyze the drag force, we should first know what's happening at the back of the pod. So The first feature which is happening is the Prandtl-Meyer expansion waves, in which pressure, temperature, and density is decreasing, but fluid particles are speeding up and Mach number is increasing, which turned into the supersonic oblique shock wave, which completely isolated the back of the pod. And the second feature is the recirculation region. When after the oblique shock wave, the small vortices are being generated and continuously merging with each other and created larger vortices, which overall decreases the pressure at the back of the pod. Here also I have an animation which shows that how these vortices are being generated. And the background is the pressure that you can see for higher blockage ratio. Overall, the pressure is less than the lower blockage ratio. And this low pressure at the back and high pressure in front will increase the drag force. That you can see the effect of blockage ratio for the drag force. As you can see that higher blockage ratio results in higher drag force, which is around 157% higher than the lower blockage ratio. Now, since we have the solution of the incident shock wave, then we can consider how to initialize the reflection shock wave. And if you look at the scenario here, when we assume that the shock hits the pod, the tube and wall and reflected back, the downstream of the shock wave is unknown. And this is the point that we use the simulation protocol to find these properties at the downstream of the shock wave. The first thing that we use is that the end wall is acting like 100% blockage ratio, which enables us to use piston analogy and all those formulas of the piston analogy. And the second point is that the downstream condition of the incident wave is identical with the upstream condition of the reflection wave. This is the reason that we first need to run the simulation to get the solution of the incident wave to be able to initialize the reflection wave. So here are the formulas. I'm not going into detail of mathematics here, but the point is that out of this formula, we are able to calculate the pressure ratio of the reflection wave. So then we have the upstream condition, then we are able to obtain the pressure downstream and all other parameters of the downstream by using these formulas. For instance, in the table, I calculated the pressure and temperature of downstream. And you can see that for both blockage ratio, after the interaction of incident wave with the tube and wall, the pressure downstream increases. And for higher blockage ratios, since the shock wave was stronger, it's producing higher pressure for the downstream. So with having the solution of the reflection wave, we can initialize it into our solver and run the simulation to see how reflected shock wave reaches to the pod, hits the pod, and upstream condition of pod increases to the higher value, neutral condition occurs, and the second shock wave, reflected shock wave, actually is being generated and moves again towards the tube and wall. And here the bullet points, I've already explained them, and jump into the drag analysis. You can see that previously the drag force was only because of the incident shock wave, which we call it incident drag. At 0.02 second, around 0.02 second, shock wave hits the pod and drag suddenly jumps to a higher value. And you can also see the effect of blockage ratio here, that the increase of drag force due to the reflection shock wave is more significant in comparison with the lower blockage ratio. And even you can see by calculating the drag coefficient, and in the table you can see that the drag force induced by incident and the reflection shock wave. And the difference between these two drag force is something around 250%, which uh, actually should be avoided, taken into account in the design and the requirements. So the second model that we use is the viscous model, where we add viscosity into our equation. We change the boundary conditions of the wall and the solution for three different time steps, as you can see. The thing is that for the viscous model, in addition to the pressure drag, we are able to calculate the friction drag due to axial shear stress acting on the pod. And the summation of these two drag force will gives us the total drag. And as you can see, as we add viscosity, we get more physical and more accurate drag force, and especially the transient behavior of the drag force. But in the table, I try to differentiate between the pressure drag and friction drag. As you can see, the friction drag is way smaller than the pressure drag, meaning that pressure is the main contributor in the drag force for these test cases. And with the same methodology for the initialization of the reflection wave, which I explained in inviscid model, we can initialize the reflection wave for the viscous model, and then we can run the simulation. And I just brought the solution of different time steps before interaction of the reflection wave, and then the first bow shock and how it turns into the normal shock wave, where at 0.3 second it almost gets stable. So what I explained about the mass flow rates and the new choke condition, actually in the first plot you see that mass flow rate were actually choked at this value for the incident wave, but when the reflected wave hit the pod at 0.02 second, mass flow rate suddenly jump in the minimum area and choked at the higher value. This higher value will result in higher pressure and higher temperature. As you can see, the shock wave is being generated is much stronger than the previous shock waves. And for having a better visualization and understanding on the drag force, I put two drag force due to incident wave and reflection wave in one plot. The black one is actually the drag force induced by the reflection wave, which almost getting stable at 78 kilonewton. And even after interaction of the reflection wave with the pod, friction drag increases, but it's still negligible in comparison with the pressure drag. For the reason that the friction drag is very small, it can be seen from the average pressure and average axial shear stress on the pod. And as you can see, the axial shear stress, they are very small numbers in comparison with the pressure drag, pressure on the pod. And at the back of the pod, you also see the decreasing of the pressure by precisely locating this pressure. You see that you can find out this amount, the large amount of pressure reduction is happening within the expansion waves. That uh, if you're looking for doing something that decrease this pressure reduction, I think that it should be within the expansion wave region. And the main effect of this interaction, we saw that reflection wave increases the drag force on the pod. But so far, our assumption was that this drag force is not influencing the speed of pod, but actually it will cause the pod decelerate and retard. We have retardation effect. And the way that we capture the deceleration effect, the retardation effect is through the deceleration frame. in pod stationary frame, and we add a momentum and energy source them, and specifically the terms that are being affected by acceleration and deceleration. And also we had to modify the parameters which are being affected as well. And here you see that the parameter Ft appears, which is the design thrust force, which lead us to different scenarios. The first scenario that I was considering is that without no consideration of the reflection wave, the way that we design the pod and the thrust force to just overcome the drag force of the incident shock wave, which is 32 kilonewton. And the second scenario, we consider the reflection wave, but only 70% of it, which is the thrust force is 55 kilonewton. And the first result, you see that the drag force start decreasing because the speed of pod is decelerating. And for the first scenario, this decrease is steeper than the second scenario, just because that the thrust force was lower. And in the velocity plot, you can see that the speed of pod was 200 meters per second, but after interaction, it starts decreasing, and the deceleration is more steeper than this in first scenario in comparison with the second scenario. And finally, the conclusion is that in invested model, we saw the effect of blockage ratio in a strength of incident shock wave, not only incident shock wave, reflection wave, and the drag force, which in my opinion, it's one of the critical points in the design, and even before the design, defining the requirements of the Hyperloop systems and the dimensions of the pod and the tube. And in viscous model, we were able to differentiate between pressure and viscous drag, friction drag, and we saw that pressure is a main contributor, and also viscosity has a very minimal effect in the shock attenuation. And in the retardation effect, we again emphasize on the effect of a reflection wave and its importance in Hyperloop design. Otherwise, the Hyperloop train or pod won't be able to operate under design cruising speed, and it will decelerate. So here I would like to close my presentation, and thank you for your attention.
Thank you very much. Another welcome, Lucas.
Thank you very much.
So you wanted to say something? Sorry for interrupting.
All fine, I guess. We all thank you for your good presentation here, Naida. Thank you very much. With that, we have a few questions that have been asked in the Q&A tool that I will bring to your attention. So the first one is, do the incident shock wave and the reflection shock wave interact with each other? And is this accounted for in your model as well?
Well, if you mean that incident shock wave, which is being generated once, and it's speeding up and moving towards the tube and wall. And if your question is that if we can consider the situation that the two shock wave is coming from two different pods, it's something that should be simulated in another way, because here we just have one pod and one tube, so the blockage ratio is uniform around the pod. But in two pods, if we are considering they are passing by each other, so the shape of the tube, of course, it would be different. And then the question of the blockage ratio, we should consider it at the beginning, that whether the shock wave is being generated or not. But this
are they maybe asking about the reflection from the wall, so the incident and the wall reflection then? if the shockwaves come together?
The shockwave is here. For my simulation, we just assume that the shockwave, the incident shockwave, which is is caused by the movement of the pod at the beginning, is being generated and is moving towards the tube and wall and is reflected back, and
Okay.
not more incident shockwave behind it.
Mm-hmm. Then there's a second question: are there any more aerodynamic shapes that would lessen the effect of the shockwaves, that would reduce the shockwave?
Here, I didn't consider the shape of the pod, but of course that if we elongate the head and the tail of pod, we would have we can decrease the pressure in front of pod, and of course at the back of the pod, the elongation at the back of the pod will cause the expansion waves will be a little bit lengthened, and then the oblique shock wave will be a little bit decreases the strength of the oblique shock wave at the back of the pod.
Mm-hmm. The third one: based on your results, which parameters would you look into as a continuation of your thesis right now? For example, the vehicle shape, the viscous layer of the pod, the compressor on the pod. What's the thing that you would want to research after this, which a problem that you've seen that you might be able to solve?
The first thing is that, of course, the shape of the pod, which should be really thinking into the most optimum way, and I mean the elongations. And the second thing is that we saw that the viscosity, when we add the viscosity to our equation, it had a very minimal effect on the shockwave attenuation. Shockwave attenuation is another topic. I wasn't focusing on it, but the topic that is about the shockwave attenuation itself, that maybe creating some other features inside of the tube which can make more turbulence and disturb the shockwave, and then decreases the strength of shockwave. So these two topics, I think that it would be more interesting.
Okay. And then another question: looking into the viscous drag model forces, the results, what about the temperature influence on the vehicle? How does the temperature influence the behavior of the vehicle, the behavior of the shockwave?
The shockwave, well, we saw that the temperature, when the pressure is increasing in front of pod, temperature is also increasing. But on the pod, if you are considering the viscosity effect, so basically viscosity effect will be more influential when you have a elongated pod. If you increases the length of the pod, then friction effect becomes more importance, and then the turbulence boundary layer, and to really resolve the increase of temperature on the pod should be evaluated, which I mean the resolving turbulence boundary layer, it's also another topic which needs a lot of time for simulations and consideration of the mesh sizes, Y plus, and really consider that what's happening inside of the turbulence boundary layer to really resolve the temperature on the pod itself.
Yeah, I guess for all of these things, we would like to see someone have something to not only simulate and model it, but also like look into the look at how it's in the real world, have some kind of more scaled model to build up to look at that, right? To do experiments. There's one more question. Based on the findings, should we design the Hyperloop pods to be altered to mitigate the effect of drag forces induced by LISW and the LRSW, ensuring the optimal performance and stability? So is there something you would change on the pod to mitigate the effects of the drag forces that are induced?
Yeah, as I said, the main thing is that the blockage ratio is always a big problem, and it's really needed to be taken into account even in pre-design, in the requirement when you are defining which diameter of the tube, which diameter of the pod you want to use. But at the end of the day, this is something that cannot be completely removed. So we have the shock wave. One way is the shape, that the pod can be elongated, especially in front of the pod and back of the pod. And the second thing is that we saw that the pressure drop at the back of the pod in a large extent is happening within the expansion waves. And the expansion waves is completely isolated the recirculation region. So a small amount of the pressure reduction is happening within the recirculation region. So in expansion waves, maybe changing of shape or using cross media there to see that how we can disturb these expansion waves and the reduction of the pressure in these areas, or how we can prevent of our oblique shock waves.
Okay, thank you very much.
Answer the question.
Thank you very much for answering the questions.
Thank you.
Guess we'll hand over to Andrea to see if we can see what's happening next time.
Yeah, exactly. Thank you, Lucas, and thank you, Nader, for the interesting talk. And yeah, so we're going to continue already next week on the 1st of November. It's also going to be Wednesday, 5 o'clock as usual. And actually, we're going to have also just one guest, but he's going to give us 2 talks. So it's going to be Richard McFarlane, and he's going to talk about the economic success for Hyperloop, where he's gonna, or he looked at the a route between Sydney and Melbourne. And the second talk, he will talk about different levitation technology. So he will do a comparison between air skis, maglev, and wheels. So I'm looking forward to seeing lots of you next week, and have a nice evening, and goodbye.